So this is the first idea, is if we can figure out where the derivatives are positive and negative, we can figure out where a function is increasing and where a function is decreasing. And we call it increasing if it's going up from left to right, and we call it decreasing if it is going down from left to right. So here we have a graph. We're going to label all the points that are maximums and minimums, and they're called local maximums and local minimums. This point here, we would call it a local maximum, because if you visit all the neighbors around that point, that guy's the biggest. In his neighborhood, he's the biggest, so we call him a local maximum. He's not necessarily the biggest in the whole function, because if you went, if you traveled a couple 100 kilometers, there's a guy over here that's bigger than him, but his neighbors don't know about that. And so around town, that guy's the local maximum. And those are still key points. And this guy over here, he's a local minimum in his town, because around him, no one else is lower than he is. So those 2 points are local maximums and our local minimums, and we know that the derivative at those points, if you drew that tangent line at those 2 red points, you would have slopes of 0. Now we're going to graph on here all the sections where f prime of x is bigger than 0 in green, and we're going to graph all the sections where f prime of x is less than 0 in blue. So if we look at the very first section to the left of that local maximum, and if you drew a tangent on that section, can you see that the tangent on this section would be positive? No matter where you would pick on that first section, any tangent that you would draw would have a positive slope. And so we can label this section in green, and sure enough, from left to right, that section is increasing. Then if we go in between our local maximum and our local minimum, any tangent that you would draw in this section, that tangent line would have a negative slope. And so we can label this section in blue, and we notice that that blue section is decreasing from left to right. And finally, the last section, any tangent that you draw there would be positive again. So we go back to green, and sure enough, that section is increasing from left to right. So we've got our green sections, our function is increasing, and our blue section, our function is decreasing. So you're going to have a positive slope anywhere where the tangent line is increasing. And you're going to have a negative slope or a negative gradient anytime a graph is decreasing. So now what we're going to do is we're going to go through 5 examples. For each of these examples, we're going to do the derivative. Then once we have the derivative, we're going to see if we can find our maximum and our minimum points. We're going to draw a sign diagram to check where things are positive and where things are negative, and then be able to sketch it. So for example, this first one, taking the derivative. No problem, 4x plus 1. Make that derivative equal to 0 because if our slope of our tangent is horizontal, we'll have either a maximum or a minimum. Now making it equal to 0 and solving is no problem. Move the 1 over, divide by 4, and you get -1/4. Once you've got that point, and we call it a critical point because it's where things change, we're going to make a little sign diagram. We're going to label our critical point on that sign diagram, -1/4. Then we're going to check our derivatives before and after. Okay? So if I plug in a value less than -1/4, sorry, like -2, into my derivative. So now the key thing that you're going to mess up on is when do I plug things into my derivative? Sometimes you're going to plug them into your original function. So this is something to pay attention to. We want to find out where our derivatives are increasing and are positive and our derivatives are negative, because they're going to tell us where our function is increasing and decreasing. So when I plug in -2 into here and I get a negative number, I don't even have to do more than mental math estimation. I can see right away it's going to be negative. I know my function is going down. And when I plug a number larger than -1/4, like 1 billion, I quickly notice that that will be positive. And so this section will be increasing. Now, if we plug in -1/4 into our graph, I believe you get, I think I tried it earlier. Maybe it's 125, I can't remember. We'll pretend that's close enough. You could do it on your graphing calculator and actually calculate the minimum to see what that would be. And according to this little sign diagram, we know that that's a minimum. Now, we knew that already because it was a parabola, and we know things about parabolas. But now our calculus verifies that we have a parabola going up like this. So what I want you to do for the next 4, I want you to take the derivative. I want you to set the derivative equal to 0 to find out where those slopes are horizontal, because those will be maximums and minimums. Local maximums, local minimums, perhaps even absolute maximums or absolute minimums. Then check the other sections with a sign diagram to see where they're increasing and decreasing. And then draw a quick sketch, type it into your graphing calculator to see how close your sketch is. I'll put up the answer for B so that you can check as you're going. Check to see if you got your derivative right. When you set your derivative equal to 0, were you able to factor that? Did you remember to factor out the common factor of a 6? And in this section for sign diagram, again, you don't have to write f prime of x greater than 0. If you just write positive, negative, positive, that's fine. So we can see the intervals where it's increasing and the intervals where it's decreasing. So some things to remember. To find out where it's increasing and decreasing, you're plugging those values that you're checking, something less than -1, like -3, you're plugging that back into the derivative. Because it's where the derivative is increasing or is positive and negative, tells you where the function is increasing and decreasing. When you actually want to find what these maximum and minimum points are, like when you want to find -1, 7, and 2, -20, those are points on the original graph. The original graph is the original equation. Y equals 2x cubed minus 3x squared minus 12x. So I plug negative 1 into my original equation to get the 7. I plug the 2 into my original equation to get the negative 20. Setting up the derivative, not bad, and the factoring's not bad because there's a common factor and then a difference of squares. And we have 3 critical points. So when we set up our number line, we set up all 3 of them. And again, pick a value in each of the sections and check them. You try something less than negative 2, like negative 3, okay? And just as a way that I go about doing these, I usually go to my factored part, so this part right here. I go to that factored part because if I'm going to try something like negative 3, I can tell that this is going to be negative, that first factor. This one's going to be negative, and this one's going to be negative. And a negative times negative times negative is going to be negative, and I know this section is going down. Rather than actually calculate things, which takes too long, I just need to know whether it's positive or negative. So if I try something between negative 2 and 0, like negative 1, I can tell this is going to be negative, this is going to be negative, but negative 1 plus 2 is positive. And a negative times a negative times a positive is going to be positive. So that section's positive. Something between 0 and 2, probably choose 1. When I choose 1, this will be positive, this will be negative, and this will be positive. So negative times 2 positives will still be negative, and that section's negative. And finally, if I tried something bigger than 2, say 10, this is positive, and this is positive. So your question you might start to wonder is, do they always switch? Does it always go positive, negative, negative? Up and down, up and down. And when there's maximums and minimums, yes. But we are going to run into some situations where it can flatten out with a horizontal 0, but then keep increasing afterwards. For example, your regular x cubed graph does that. It flattens out completely, and actually the tangent right here is 0, even though it stays increasing. So then once we find that, we know where it's increasing, we know where it's decreasing. We can find those points. If we plug in 0 into our original equation, that's pretty easy to figure out. You get negative 3. We plug in negative 2 into our original equation, and you're going to come up with negative 19. And you can see where things are increasing and where things are decreasing. And quite accurately, you can draw an x to the 4th graph. Once you've got those maximums and minimums, and you know where things are increasing and where things are decreasing, from grade 12 last year, one of the things you might have learned was it's an x to the 4th graph, which is an even graph. Even graphs all act sort of like parabolas. And since it's a positive value in front of the x to the 4th, it's going to start at the top here. It's going to end like that. But what happens in the middle here is what we don't know. And now that we've got our calculus, we can find out where those maximums and those minimums are and be much more accurate than we were last year. All right, try the 4th one. The derivative is going to be a little bit more difficult because you're going to have to use quotient rule. So how did you do with the derivative? And then with that derivative, now we will need to simplify a bit, because if we're going to find out where it's equal to 0, simplifying it will be helpful. A couple of other things that are going to come into play with this one is we have a couple of non-permissible values. So at x equals positive 1 and x equals negative 1, we have some non-permissible values. Those two will be critical points, and we're going to add them on to our number line when we make our number line. Now, whenever you have a fraction and you're trying to figure out when is that fraction equal to 0, a fraction is only equal to 0 when its numerator is equal to 0. So we just have to worry about where 6x, which is the numerator, where that's equal to 0. And that happens when x is 0. So when we go to our number line, we're going to put 0. We're going to put our non-permissible values of negative 1 and 1 on there. And then we're going to check where things are increasing and where things are decreasing. So what's this going to look like? Well, where we have those non-permissible values, and we can label them right on here, we're going to have asymptotes. So at x equals negative 1 and x equals 1, we have asymptotes. Something from rational functions from grade 12. How do I know that there is a horizontal asymptote at y equals 1? So what we're basically asking, what happens when x gets really, really, really big? Because that's where we're going to have a horizontal asymptote. In other words, we're asking, what is the limit as x goes to infinity? And as x gets really, really big, the only thing that's going to matter are the highest powers on the top and on the bottom. And so if we just look at x squared divided by x squared, well, that simplifies to 1. And it's going to get closer and closer and closer to 1. Because as x gets bigger and bigger and bigger, minusing 4 or minusing 1 won't matter. It's like playing Monopoly. When you're at the end of the game and you've basically won, and someone lands on Baltic and they owe you $4 because you haven't put hotels on there yet, you're like, don't worry about that. Right? Because it doesn't matter. Because you've got millions of dollars already. That extra $4 is not going to bother you. At the beginning of the game, if you own Baltic and the first time around the other player lands on there, you're like, yeah, you owe me $4, pay up right now, because it's really important. So that's the same idea here. As x gets really, really big, that negative 4 and that negative 1 don't matter because the values are so large. And if we just look at the highest power on the top and the highest power on the bottom and look at that limit, you're going to have an asymptote at 1. So the only value here, because 1 and negative 1 are non-permissible values that you can plug in as a max or min, is 0. Plug 0 into our original equation, we get 4. And then from our arrows, we know that it's decreasing and increasing between those two asymptotes, so it sort of looks a bit like a parabola. In this first section, left of negative 1, it's got to be decreasing. So the only way that can happen is if you started at your asymptote and went down to your other asymptote. And for it to be increasing when it's greater than 1, the only way that could work is if you start at your asymptote and go up towards your other asymptote. So we have to, with calculus, it gives us information, but then we also have to use sort of some common sense, is with asymptotes there, how would that be possible? And our final graph, another cubic graph, not too bad. Derivative is straightforward. We get x is equal to 0. The reason we have this cubic graph is because I want to show you, like I mentioned before, that it is possible to have something where it stays increasing. even though that point in between, it's not a non-permissible value. So in the example before, we saw 2 increasings in a row or 2 decreasings in a row, but we had an asymptote in between. This is a continuous function that's always increasing. What does it look like? Well, an x cubed graph, if you plug in 0, you're going to get -5. It flattens out right here, because you know what an x cubed graph looks like. I mean, going to our transformations, this one would have a vertical stretch by a factor of 2 and then have been moved down 5 units. But we still have a place where it flattens out. That's that shape of that x cubed graph, even though it was increasing all the way.